So as we have seen in the previous lessons, how to create and manage machine learning project. And this lesson will focus on the taking an example of building a heart disease prediction machine learning project. We'll start with the key steps of the theory behind the steps involved on managing and creating the heart disease machine learning project. And then we will go to the coding part, which involve real world data as well as creating a model that could help predicting the heart disease. I'll walk you through each step of building a machine learning project using the example of predicting heart disease from clinical data. I'll cover everything from defining the problem to deploy the model into the production. So, as we have discussed in the previous lesson, the first step that we have here is to define the problem. As we say that every successful machine learning project starts with clear understanding of problem that you're trying to solve. In this case, and in our case, we want to predict whether a patient has heart disease based on clinical data such as the gender or age, blood pressure levels, and cholesterol levels, ECG results, and many more data. A key consideration here that we have to understand the business objective. So in our case, the business objective here is to identify patients at risk for heart disease so the doctors can take a preventive action. Next, we have to identify the type of problem. As you've guessed right, that we are trying to predict whether a patient might have a heart disease or not. So it's yes or no problem, or we call it as a classification problem, where we are predicting a binary outcome, which is yes or no. Also, we have to identify the evaluation metric, how our model is going to be evaluated. So in our case, we will choose the main evaluation metrics that is involved on a classification problem, such as the accuracy, precision, recall, F1 score, and ROC and AUC to handle imbalanced data. After we have defined the problem and we understood the business objective behind building the machine learning model to predict the heart diseases for patients, and we understood the type of problem as a classification problem, and then we defined the evaluation metric that we are going to measure our model accuracy and precision and recall based on. So the next step here is the data collection and exploration or understanding. The next step here is gathering the data. In the case of heart disease prediction, the data could come from patient records of public datasets like Cleveland Heart Disease Dataset. The data should contain clinical attributes such as the age, the gender, the blood pressure, cholesterol level, and other relevant medical information that is highly correlated with the heart disease problem. The key action involved at this step is collecting the data from a relevant and reliable source, ensuring that your data comes from a well-trusted place such as a clinical data or a hospital data or a medical database. The next action that we have to take is understand the feature included in the dataset. And then we have to explore the available labels or variables, such as the target variable and the dependent variable and independent variables. The dependent variable, which we call it as the target variable. In our case, the target variable is yes or no, as we mentioned, it's 1 or 0 prediction. One mean yes, he might have a heart disease, and zero, he might not have. A real world example here. Using the Cleveland heart disease dataset available on UCI machine learning websites, which contains several attributes such as the age and the gender or sex, chest pain if he has, yes or no, and then resting blood pressure, serum cholesterol levels, maximum heart rate achieved. So after we have collected the data and we have understood the key features and the target variables and the type of problems that we are trying to solve, and we identify the key um, independent variables or features that could help us building a model with a higher accuracy percentage, then the next step here we have to take is the data pre-processing. Before building a model, we need to pre-process the data to ensure it's clean and ready for analysis. This is often one of the most time-consuming steps. The key action here involved in data pre-processing first is handling missing data. When you check for any missing values and decide how to handle them, either by imputing values or removing the rows and columns. It all depends on the data that you have on hand. Next, we have the feature engineering. As we mentioned in the previous lessons, feature engineering uh, means creating a new features or transform existing ones to improve the model performance. For example, encoding categorical variables or scaling numerical data. Next, we have the outliner detection, meaning to identify any extreme outliners in the data that could negatively impact the model training. A key step here, which called the data normalization or standardization. Standardizing the numerical features like age and cholesterol level to have a zero mean and unit variance, or normalize them to 0 and 1 range. Once the data is pre-processed, including removing outliners, duplicates, filling, imputing the null values, we split the data into training and testing sets. The training set will be used to train the model, and the test set will be used to evaluate its performance on unseen data, a data that the model hasn't seen before. The key actions involved when splitting the data is train test split. Typically, we use 80-20 split, where 80% of the data is used for training and 20% is used for testing. But sometimes you might see in developers that they split their data into three split, including a third split, which is called validation with a 15%. So they might do it as 70% for training data and 15% for validation data, and then 15% for testing data. Also, the stratified sampling. If the data is imbalanced, example of the heart disease problem, when you see more non-heart disease cases than heart disease cases, using Stratify sampling to maintain the distribution of target variable in both training and testing set. With the data being prepared and we completed splitting the training and testing data sets, it's the time to select a machine learning model. The choice of model depends on the type of problem you're trying to solve. In our case, for heart disease prediction, we could start with a few commonly used algorithms for classification tasks. Here are some possible models for classification problem. The first one is logistic regression. It's a good start point for binary classification problem. In our case, we are trying to identify whether a patient could have a heart disease or not, yes or no. Next, we have random forest. It's a powerful ensemble method that can handle complex nonlinear relationships. We also have support vector machine, which is SVM. It's effective for high dimensional data. One common algorithm used for classification here is k nearest neighbor, which is KNN. It's a simple, innovative model that can work well for small to medium data set. Let's talk about an important concept when selecting a model to solve your problem. Experiments play a crucial role in choosing the right model to solve a classification machine learning problem. The process of experimenting with different models is essential for different reasons. Since different machine learning models have different strengths and weaknesses, some models may be well suited for particular problems with different data characteristics, while others may struggle with finding patterns within your data. So, experimenting and iterating through this process allows you to find the one that best matches the characteristics of your specific dataset. And also, it's important to talk about trying different models and performance, doing a performance comparison. Each model has different performance metrics such as the accuracy, precision, and recall. And some models might perform better depending on the data distribution or class imbalances. Through experimentation, you can evaluate multiple models using cross validation to ensure that your data generalizes well with unseen data. Also, it's important to compare different performance metrics to decide which model best meets your goal, as well as identifying models that overfit or underfit, depending on the amount of training data that you have.